Ohm's law. When people, unaware of the current leakage from an electrical appliance, accidentally touch it, they experience a sudden jolt. The shock can be fatal if the volt source is as high as 110. However, the impact of the shock felt is almost negligible in case of an extremely low voltage, say as low as 6 volts. Do you know why? In these two examples, for different voltages, the electric current flowing through the body is different. Let us understand the law governing the relationship between the current and the applied voltage. The law is known as Ohm's law. We will study and verify Ohm's law. George Simon Ohm was the first scientist to articulate a mathematical relationship between voltage and current, famously known as Ohm's law. Ohm's law states, at a constant temperature, the current I flowing through the conductor is proportional to the applied voltage or potential difference V across it. Mathematically, it can be expressed as I is proportional to V. V over I equals R, where R is the proportionality constant called the resistance of the conductor. From the given equation, resistance is defined as the ratio of the applied voltage to the current that the conductor carries. R equals V over I. Since voltage is measured in volt and current is measured in ampere, the SI unit of resistance is volt per ampere, which is called ohm, in honor of the scientist George Simon Ohm. It is denoted by the Greek alphabet omega. Let us perform an experiment to understand Ohm's law. Connect a bulb and an ammeter to a variable voltage source in series. A key is connected to on or off the power supply. A voltmeter is connected across the bulb. The applied voltage can be varied from 0 to 12 volts. For 0 volts applied, there is no current and the bulb does not glow. Now, gradually increase the applied voltage. The ammeter indicates the increase in the current. As a result, the bulb starts glowing more brightly. For different applied voltages, measure the corresponding values of the current. Now, plot the graph of the applied voltage versus current. The plot of current I versus voltage V is seen to be a straight line passing through the origin. The ratio of the applied voltage V to the current I equals R in all the cases. This constant R is the resistance offered by the bulb and is given by reciprocal of the slope of the straight line, indicating a linear relationship between current and voltage. Let us place another bulb and repeat the above experiment. We again get a straight line, but with a different slope. This experiment clearly proves the Ohm's law. Hence, Ohm's law shows that a given voltage can push more current through a lower resistance, or vice versa. Coming back to the question posed earlier, why there is a variation in the intensity of the electrical shock in the two cases, here is an explanation. The human body behaves as a conductor. The resistance of the skin varies from 1000 ohms for wet skin to over 500,000 ohms for dry skin. When the 110 volts AC voltage leaks into the body of the toaster, as per the Ohm's law, the current flowing through the wet human skin is 110 volts over 1000 equals 110 milliampere. This current can give fatal shock. In the case of 6 volts generated from a mobile charger, the current passing through the human skin would be 6 volts over 1000 equals 6 milliampere, which would not cause fatal shock. Ohmic and non-ohmic devices. Does every device obey the Ohm's law? No. Those which follow the law are said to be ohmic devices. Those which do not follow are said to be non-ohmic devices. Metal conductors, resistors, hairdryer, etc. are the examples of ohmic devices, whereas devices such as diodes, thermistors, vacuum tubes, transistors are the examples of non-ohmic devices. Summary: at a constant temperature, the current I flowing through the conductor is proportional to the applied voltage or potential difference V across it. Resistance is defined as the ratio of the applied voltage to the current carried by the conductor. For ohmic devices, the plot of current I versus voltage V is a straight line, indicating that the relationship between current and voltage is linear, while for non-ohmic devices, the relationship is a non-linear one.